All right. Well, we're very happy to have Michael Kim here today from Cornell University. Michael did his PhD at Stanford, and then were you at Berkeley at any point?
Mm-hmm.
You were at Berkeley doing a postdoc, right?
Yes.
Yeah. And Michael's done a bunch of things. I mean, at least two papers that I know of that I have read from time to time has been his work on multi-calibration, his work on outcome indistinguishability, and I see that here, so we'll probably hear a little bit about that today as well. And we're very glad to have you here. So
Thank you so much. All right, great. So, I'm Michael Kim. Tell you today about some very recent works on Omniprediction. So, it's near optimal algorithms from Omniprediction. This is joint work with Princewell Okoroafor and Bobby Kleinberg. Feel free to interrupt me at any point. I have a bunch of slides, but I'd much rather get through half of them and have you understand a lot of them than to get through all of them and have you understand none of them. So great. So this is and there will also be some coverage of this other work that appeared at ITCS, I guess last year. Good. So what's the plan for today? So hopefully I'll be able to tell you a little bit about all of this on achieving what we near optimal algorithms for this idea of omniprediction. I'll start by introducing the omnipredictors problem, motivating it, tell you about what's been done, and tell you our results. And then I'm going to get into sort of how we get these results. Okay, we'll go through a concept that we call outcome indistinguishability, a new concept that we call proper calibration, tell you a little bit about that, and time permitting, I'll get into how do our algorithms actually work and what do they look like. Okay, so to start, let's talk about omnipredictors. Okay, so the motivating perspective here for this line of work is that predictions inform the decisions we make. Okay, so by prediction, I mean sort of in a supervised learning framework, given some features X, make some prediction about an outcome Y, right? So maybe the quintessential motivating example is given today's weather conditions, what's the probability that it will rain tomorrow? Okay, that is a well-posed prediction problem. What's the probability it will rain tomorrow? Binary outcome. But really, many different, we might want to make these predictions for many different reasons, for many different decision makers, right? Should I bring an umbrella on my walk to work? Is it a good time to plant seeds or harvest or, basic, lots of agricultural and people care about the weather patterns. And, maybe a different, is it going to be safe to run my bike race? You name it. There's a bunch of different decisions that you might want to make based on some prediction, each with a different characteristic of like what is the cost and benefit to making the decision given a prediction. Okay? The classic notion of learning, though, is sort of with respect to a fixed singular loss function. Okay, so this is the loss minimization framework where you try to find a best fit predictor, right? So given a loss function L and a hypothesis class H, this is a class of prediction functions, and some accuracy parameter epsilon, you want to find a predictor P that minimizes this loss function, minimizes the expected loss with respect to this hypothesis class, right? So you want to find a predictor P that achieves loss that is no bigger than the minimum achievable within H plus some small epsilon, right? This notion familiar to people? If not, hopefully you can follow along. But this is like the, in many, machine learners' eyes, this is the definition of learning, basically, right? Is minimizing a loss function. Okay. The challenge, of course, or the critique of this framework, despite this is what drives all of the progress in machine learning these days. This is loss minimization. But a critique of this framework is the following. so if you get a new decision maker, you get a new loss function. So what does that mean? The classic and traditional belief is that given a new loss function, I need a new predictor. So just retrain, give me a brand new loss minimizer. Okay, so this is costly, and a question you might ask is whether there's an alternative. Okay, this is the motivating question behind Omnipredictors. Is it possible to learn a single predictor, one predictor to rule them all, that is a simultaneous loss minimizer for many different losses at the same time? Okay, so let me tell you what that means formally. But intuitively, I'm going to try and learn a single predictor that somehow gives me the optimal decisions for many different losses simultaneously. Okay, so this was a really provocative notion introduced by Gopalan et al. A few years back. What does it say? It says that for now, I'm going to not give you a single loss function, but a collection of loss functions. This capital L. So a loss class, a hypothesis class, and still this epsilon parameter, this accuracy parameter. I want you to find a predictor, P, such that for every loss in my class, this predictor achieves the loss minimization guarantee. Okay? If you think about that for more than a second, you should say that's not possible. Okay? Because different losses encode different optimal decisions. For instance, if my loss is based on the squared error, then the best thing I can do is predict the expectation of y given the features x. If my loss is the absolute error, the L1 error, then the best thing I can do is predict the majority, the median instead of the mean. So round my probability to 0 or 1. Okay, so there's something not right here. So that's why I'm going to allow this, I'm going to cheat and allow my predictor to have one advantage, and that's that it's allowed to post-process this prediction according to a best response rule. So basically what it says is that this Omnipredictor definition expects a probability estimate. Okay, it expects a probability estimate, and it asks you, what is my predictor then going to do? It's going to say, take in this probability estimate and best respond to the probability estimate according to my loss function. So that's this KL function. It's a univariate optimization that for most loss functions is explicit and very easy to compute. So I'm just going to say it's a type checking post-processing.
But KL doesn't depend on P in particular.
KL does not depend on P. If you tell me L, I can tell you KL, right? And typically it's very efficient to compute. Okay. So what this means is that there's no retraining necessary. If you can achieve this definition, then for every loss in the class, P encodes the optimal decisions. Because given some L in the class, I know what KL is, and I can just compute KL composed with P. Okay, and just so that we're making sure that we're all on the same page, if I took this capital L to be a singleton, then I just recover the loss minimization guarantee. Okay, any questions on the definition of Omniprediction? Yes.
So Px is a scalar?
Px is in the interval 0, 1. You should think of P of x as an estimate of the probability of y equals 1 conditioned on x. And that's often our goal in prediction, that this gives us a specific form of kind of test that we need to pass in that estimation procedure. Yes?
Does P need to belong to H or it's improper?
Say, come again?
Does the predictor need to belong to the hypothesis class?
Great question. So the question is whether we care if it's a proper learning algorithm or not. We're going to, we care about the complexity of P, but we're going to allow P to sit outside of H. Ideally, though, we would want P to be as close to living in H as possible. Really good question. Yes?
Is KL independent of the loss class L?
KL is uniquely determined up to let's not say uniquely, is determined by L. By little L. So each KL is derived from little L. So for each little L in my class big L, there will be a different KL. Yeah. So for instance, going back to the squared error, in the squared error instance, KL will be the identity function. And for the L1 error, KL will be round to 0 or 1.
I think one question would be that does it depend on capital L? If you have capital L and capital L prime, and they have some intersection, would the KL then look the same for that thing in the intersection, or would it depend on capital L?
Yeah, so KL is determined on a per little L basis.
Okay, so it would be the same
Yeah.
as that point.
It will be the same one. There's some, this KL is formally defined as an arg minimization. So if that's not unique, then there isn't a unique KL. But up to sort of tie breaking basically, it is unique and uniquely determined by little l. So the cardinality of the KL that I need will be the same as the cardinality of capital L. Great. Happy to take more questions. We shouldn't move on until this definition makes sense.
So what prevents me to make a predictor that, depending on every single loss, just schemize a different part of I select based on the loss what minimize a different function for each with respect to each loss, and then KL just selects the region where I make the prediction, the prediction with respect to that loss. So based on the
So definitionally, nothing prevents you from doing something very complicated here, right? That you could memorize the loss minimizer per each L, and now build a huge lookup table, and say, okay, you've given me L. Okay, look up what the prediction. Yeah, definitionally, there's nothing wrong with that. I'm going to be concerned about efficiency. Right? Yeah. And in fact, this KL is going to be much simpler than look up the value. It's going to be post-process, assuming that you gave me the true prediction of y given x.
I guess I don't understand the role of capital L then. Because the definition seems to work, especially since KL only depends on small l. I don't see what big L is doing at all in this definition.
Because I'm getting it for all L in big L.
Right, but
He's saying you get to choose K.
okay, once you see the construction, maybe it'll be clear.
Yeah, I'm happy to right. I'm gonna so in particular, I'm gonna show you how to achieve this for clauses like all convex loss functions. So an uncountably infinite number of loss functions simultaneously. So even for that, lookup tables aren't going to help you. But definitionally, hopefully it makes sense. We want a simultaneous loss minimizer for all little l, all losses in our big class, and we want it to somehow be encoded and compressed into this single predictor P of x. If there's more questions as we go, you should ask them, but I'm going to push on. So the question you should ask is, do efficient omnipredictors exist? It's not obvious from the definition that you can achieve these things efficiently. But in fact, from the original work on omniprediction, they showed that you can. Okay, so these omnipredictors do exist. Not only do they exist, but you can achieve them efficiently. Okay, that is to say that, and so the way they showed this was that a certain construction of multi-calibrated predictors are actually omnipredictors. Okay, I'll talk a little bit later about what this notion is. But what the consequence is, sort of keep a report card on how we're doing on these Omnipredictor constructions throughout the talk. The upshot was that you can implement these Omnipredictors efficiently. Okay, they're implemented by small circuits computed from a small collection of hypotheses from H. Okay, so it's not a proper algorithm, but it's a combination of not too many copies of H from our hypothesis class. You can learn them in a small sample complexity, and you can achieve them using an agnostic learner for this class H. Okay, so sort of this is a pretty sweeping efficiency result. You can learn these things. You can achieve it for all convex Lipschitz loss functions. Okay, I learn a single predictor, gives me a probability function. Then for any convex loss function, I can post-process the prediction to give me an optimal decision with respect to this hypothesis class H. Okay, subsequent work that I was involved in refined this and gave sort of a more direct construction from a condition we call multi-accuracy and calibration for very general classes of loss functions, even more general than convex loss functions. Basically all Lipschitz loss functions, you can do this. And I'll talk about this construction later in the talk. Okay, but the thing that I want to focus on is actually this sample complexity. Okay, so I'm saying this is great, this is efficient, but really when you uncover what this poly is, it's actually quite big. Okay, so in particular, there's this question of like, what is actually the complexity of achieving omniprediction? Okay, and how does it compare to standard loss minimization? Okay, so we know that the optimal rate of the statistical complexity of loss minimization is some dimension of this hypothesis class divided by epsilon squared. Okay, that's the optimal rate of learning. What we have for omniprediction so far is something much worse. It's, the epsilon dependence goes as 1 by epsilon to the 10. Okay? And so there's a question here. Omniprediction is a much stronger guarantee. Right? It's a guarantee that you get for an uncountably large class of loss functions. It stands to reason that maybe there's an inherent gap in the complexity between these things. Maybe actually achieving omniprediction requires more samples than standard loss minimization. Or can we tighten this gap? Okay, and that's what we study in this latest work. And we show that, in fact, there's essentially no gap. Essentially, you can, up to very small order terms that we have some belief that we can get rid of, or, we'll see. It's up to small order terms. We achieve omniprediction in nearly loss minimization complexity. Okay, so what is this first result that I'm saying? For any loss class in an incredibly huge collection of loss classes and any hypothesis class, there exists a learning algorithm that for any fixed distribution D and any epsilon greater than 0 returns an efficient, in this case randomized, omnipredictor for the class L, H, and this error parameter epsilon using nearly optimal samples. Okay, some dimension of our loss class and hypothesis class. If you're familiar with VC dimension, we're working with real valued functions, so it's not the VC dimension, it's some kind of fat shattering dimension, but you can think of it as VC dimension divided by epsilon squared. Okay, and I think there's a log 1 over epsilon in here too, is what's hiding in this O tilde. So really very close to the optimal bound for minimizing even a single loss function. Okay, any questions on the statement of the result? Okay, in particular, one thing that's important here is that we're producing efficient omnipredictors. We're identifying it in a small sample complexity, but we're outputting a predictor that can be computed by essentially evaluating, again, 1 over epsilon squared copies of a function, of a hypothesis from H. It's not very improper. Say a linear threshold of combinations of hypotheses from the class H.
So the L circ H, right? I mean, I'm thinking of your KL circ PX. PX did not have to be in H. It could be a
That's right.
definition, but here it sounds like it will be.
So P, the Omnipredictor, won't exactly be in H, but it will be computed by a few copies of functions from H. Yeah, exactly. It's great. Great question. Was there another one?
That bounded variation something critical, or why have you required this?
Why do I need it? It is pretty critical. It basically says that you could think of this as Lipschitz, you could think of it as bounded variation. It's basically saying that you need to be able to reason about basically the losses outside of bounded variation will be extremely high frequency losses that basically if you don't see the changes in them in a small sample. Okay, so really this is about as general as you could hope for. Alternatively, though, if you had a basis that your losses decompose into very high frequency functions, then you should be able to use that basis instead of the one that we use. So.
But convex losses, you could have some pretty high variation. I mean, maybe I'm not interpreting variation.
No, yeah. So this includes the class of bounded convex functions.
So bounded secondary. When you say bounded, you
I mean bounded in magnitude. Yeah.
Is the O tilde different than a regular big O?
Yeah, I'm suppressing a log 1 over epsilon factor here. Good question. Okay, so in fact, it doesn't say it in the theorem, but I can make this algorithm oracle efficient in the sense that technically weak agnostic learning, or agnostic learning period, is a hard computational problem, okay? And so we're doing some form of agnostic learning, so there's no way to get around that. What we're saying is that computationally the only thing we need is this agnostic learner, okay? So I can make this so that if you can agnostic learn or if you can run an ERM oracle, then this is computationally efficient, not doing something beyond that. Okay, in fact, where does this result come from? It actually comes from an online algorithm that we give. Okay, we study this problem in the online learning setting, and we show that there's a way to achieve bounded regret with respect to this omni-prediction objective. And this one, too, we can make oracle efficient in some online sense. Good. So the report card of our algorithm and our construction is that we're able to achieve this omni-prediction guarantee, this very strong loss minimization guarantee, simultaneously for all losses in a ginormous class of loss functions, roughly at the price of minimizing a single loss function. Okay, where you produce predictors that are not very hard to compute compared to the hypotheses you're competing against. The sample complexity is near optimal, and the learning complexity is near optimal too, or is basically what you need to do learning. Okay. Yeah, interestingly, exactly what oracle you end up needing changes depending on the types of loss functions that you want. And so actually convex losses are easier in some sense than achieving this guarantee for all proper losses. Okay, so that's sort of the statement of the results. I want to get into this idea of outcome indistinguishability and sort of tell you how we might hope to achieve this notion of learning. Okay, because it's going to come from a paradigm that doesn't look like your standard loss minimization. Okay. So in particular, we're going to try to view this learning problem through the lens of computational indistinguishability. Okay, so computational indistinguishability is huge in the crypto and complexity world. Hasn't been thought about so much in the learning theory world. Okay, and so the goal, in some sense, is that we want to learn a predictive model that looks like nature's predictive model, in some sense that we'll make formal. Okay, before making it formal, I'll give you, it's best explained by the following game. Okay, and this is from a work with Dwork et al. That appeared a few years ago. Okay, so how's this game going to go? The game's going to go as follows. I'm going to present to you a triple, an input, a prediction, P of x, and an outcome y. Okay, it's outcome indistinguishability, so something about this outcome is going to change. I'm going to promise you that the outcome is drawn from one of two worlds. Okay, nature's world and my predictive models world. Okay, in nature's world, the outcome is sampled as a true outcome, as like one from it rained yesterday or not. Okay, in the modeled world, I'm going to sample the outcome according to this probability that I presented to you. Okay, according to this p tilde of x, you get y tilde. Okay? Your job then is to guess which world we're in. Okay? I presented this triple x, p of x, and y, and your job is to guess whether y was sampled from nature's world or the modeled world. And intuitively, at least, we say that a predictive model is outcome indistinguishable if you can't win this game. Okay? If you can't reliably tell whether the outcome was sampled from nature or from the model of nature. Okay, that's the intuition. Let me write down an actual definition for you. Okay? So I'm not actually going to, although I believe that you all are esteemed distinguishers, I'm not going to rely on just the audience to distinguish. In fact, I'm going to parameterize this guarantee of outcome indistinguishability by a class of algorithms. Okay, so capital A will be a class of distinguisher algorithms, and I want it to hold that for all little a, distinguisher algorithms in this class of algorithms, I want it to be the expected behavior in nature's world and in the modeled world is basically the same. Okay, what's the difference between these two distributions? The difference is just in the conditional distribution of the outcome, conditioned on x and on the predictor. Okay, here y is sampled from nature from the true distribution of xy pairs. In this other version, in this DP, this is the modeled world where I'm resampling y tilde as Bernoulli of my predicted probability. Yes, question?
Sorry, so A maps from this tuple to what?
Yeah, great question. So A you can think of as mapping to 0, 1 to the could output a real value. It's a bounded function, let's say. Yeah. And there's some mapping, that without loss of generality, if you allow randomized distinguishers, you can think of them as mapping to binary predictions, sort of guessing whether it's nature or the model. Okay, where alternatively, because I'm taking an expectation. Okay, otherwise it would just this expectation is maybe the probability that it outputs a 1 or a 0. Yeah. Good question. So yeah, this predictor would be outcome A epsilon outcome indistinguishable over this distribution D. So the only thing that's changing here, the marginal distribution on X is staying the same. The only thing that changes now is the conditional distribution of y given x. And in the modeled world, it's, I'm telling you what that probability is. I'm telling you what the distribution on y tilde is. Okay, so this kind of test, it turns out we can turn into a pretty powerful learning framework. So this outcome indistinguishability is actually equivalent to this notion of multi-calibration that I talked about earlier. And what it says is that basically you can turn this kind of indistinguishability condition into an algorithm, into a learning algorithm to produce predictors that fool these tests, that pass all of these tests. And so if you can write down your learning objective as some kind of outcome indistinguishability, then I can give you a learning algorithm that will achieve it. Okay, let me make this a bit more concrete in talking about the Omniprediction problem. And then we'll see if there's still questions. Okay, so what I want to show you is that you can define a set of outcome indistinguishability conditions. We'll call it loss outcome indistinguishability that achieves omniprediction, that implies omniprediction. Okay? So let's think about what this omniprediction condition is. It says that for every L in my class L, for every hypothesis H, I get that the loss of my predictive model after post-processing is at most the loss under achieved by this hypothesis. Okay? So somehow, if I want to turn this into an outcome indistinguishability condition, these are the expectations I need to reason about. Okay? So I'm going to define a class of distinguisher algorithms in terms of these loss functions. So let's look at it. Okay? So we want to derive an inequality about these losses in the real world. That's what we're after. We want to say that this thing is less than this thing. How are we going to do that? We're going to do it by trying to go to the modeled world where we can understand things more clearly, where we know what the distribution of the outcomes is. And so that will allow us to make some really easy and straightforward inequalities there and bring them back up to the modeled world. Okay? So in particular, if I have this expectation and this expectation in the real world, then I want to be able to reason about these expectations with respect to the modeled world. Okay, so that's what I'm writing down here. I'm writing down two classes of distinguishers that induce some OI condition that says I want that my expectation of this loss with respect to the hypotheses in the real world to equal the loss in the modeled world. Similarly, I want this loss with sort of my self-loss, the loss I evaluate on my own predictive model, to be the same in the real world and in the modeled world. Okay? So then, once I have this, and I'll show you on the next slide, once I have this, allows us to go to the modeled world. Okay, so the first condition, this hypothesis OI, exactly allows us to relate this equation, this expectation, to this expectation. Similarly, this decision OI allowed us to relate our decisions in the real world to the loss in the modeled world. Okay, and now I get to reason about everything in the modeled world. Okay, in particular, in the modeled world, outcomes are sampled according to my predictive model. So my predictive model is the statistically optimal thing to make decisions based off of. I know what the Bayes optimal predictor is in this world. Right? I can't do better than using my predictive model because the outcomes are sampled according to my model. So this KL composed with P is actually the statistically optimal prediction according to this loss L. So that means no matter what I had over here, this expectation is less than that over there. Right? There's nothing I could do that would be better than this predictor. Okay? And that's the proof. That means that because of these equalities, I get to bring this inequality back up into the real world. Okay, so I think this idea of outcome indistinguishability, it takes a moment a few months to like really squint at and understand like what it's doing. But once you internalize it, then proofs of this form like just present themselves over and over again. It's like a really clean way to go from I want this property in the real world. I want like a guarantee, this kind of statistical computational guarantee, write down a set of tests that I need to pass, and therefore I can reason about them in the model world and prove that this thing, my model achieves this property in the real world. Okay, so if you take nothing else away, at least take away that the proof fit onto one picture slide, and like maybe that suggests it's a powerful framework to think about. So any questions about what I did here, or the proof, or the what we're doing here?
Just so I understand, using two copies of OI,
Yes.
go down from top to bottom, and you're using as you said, the fact that in the model world you know exactly what's going on to get that inequality.
That's exactly right. So the point is that in my right column, I have distinguishers. I have tests that I introduced that I called these hypothesis OI, but it's just that I've defined certain tests based on the loss and the hypotheses in H. And so that means I can equate the right column. I had a separate set of tests that I used to equate the left column. So I'm applying OI in both of those cases to get this equality, and then my inequality is derived, as you said, just based on what I know to be true in the modeled world.
Where does the Lipschitz property come into play? Later on when you do the sampling?
Good question. So where does Lipschitz come into play? Lipschitz comes into play in actually estimating these things. So technically, I want this hypothesis OI and I want this decision OI to hold for every L in L. And I promised you that I'm going to achieve this for uncountably many L in L. So I better not be enumerating enumerating each of the distinguishers that I need here. In fact, given properties of the loss function, of the loss class, you can derive a basis for this class of functions and just define a set of distinguishers based on the basis. And so Lipschitz loss functions have a basis in terms of threshold functions, and we use that. Great question. Yes?
How did you posit these epsilon approximations? Or you actually numerically check?
We can give there for a fixed finite epsilon. I can give you an algorithm that learns that learns a predictor p that satisfies each of these equalities and therefore satisfies this inequality. Yeah, and my complexity of learning will depend on epsilon. But yeah, we can actually achieve this. Yeah, with high probability over the sampling and such. Yeah. Good. So what I showed you here is that a way to achieve omniprediction via this loss indistinguishability, outcome indistinguishability framework. Okay. In fact, we can, when you squint at these outcome indistinguishability conditions, you can actually turn them into conditions of multi-accuracy, a notion that we've studied previously, and calibration. Okay. And so the main thing that I want to talk about in the remainder of the time is actually this calibration condition. What it is and why it's good, why you might want to avoid it, as well as what we do instead of this calibration. Okay? Okay, and that's this notion of proper calibration. Okay, so calibration is a concept that's been studied it's been studied for a long time in the forecasting and probability world and online decision-making world, but it's recently come into focus in discussions about fairness in prediction and just prediction quality. How should you think about calibration? Calibration, to me, really means that predictions mean what they say. Okay, what do I mean by that? I mean that when my predictor says V, okay, when it says that the probability of rain is 50%, then it actually is the case that 50% of those days it rained. Okay, so it's sort of an unbiasedness condition, conditional on my predicted value. So if I say that it's 50-50 every day, and it rains 50% of the time, that is calibrated. But really, I want sharp calibrated predictions. If I say 80% of the time, then it actually has to be the case that on those days that I said 80% of the time, it rains 80% of the time. Okay? Now we're going to have, to appreciate our contribution in this latest work, we have to talk about this approximately equal sign. Okay? Just a sneeze? Okay. If there was a question online, happy to take it. Okay, so what is this approximately equal? Typically, the traditional definition of calibration is so-called L1 calibration, or expected calibration error. It says that my expected error, when I draw a prediction from the supported range, that the average L1 in absolute value error from what I said the predictions were to what the expectation actually was is smaller than or equal to epsilon. Okay. This notion, it turns out, is sufficient for decision OI. Is it sufficient to give omnipredictors? Question is whether it's necessary. Okay, so let me draw a picture of what I mean by this L1 calibration. Okay, so this is a calibration curve. Okay, I have my predicted probability on the x-axis and sort of the true probability, or this expectation of y given prediction, on the y-axis. Okay, so a perfectly calibrated predictor would have the blue curve here, right? Straight slope one line. But maybe I have some prediction in orange. Okay, let's try to evaluate what the calibration error of this predictor would be. Okay, for L1 calibration, this traditional notion of calibration, I need to look at the area that I'm incurring error, right? And in fact, what am I going to do? I'm going to take the absolute value of this error. So for L1 calibration, this error sums up in an absolute sense. All of these blue regions contribute positively to the L1 calibration error.
How are you measuring each error? Not the area you said.
I'm
being loose.
I'm being loose.
Okay, fine.
Really, you need to discretize these predictions, right, to be able to reason about what is this conditional expectation.
Yeah.
But morally, maybe I should have drawn them with rectangles instead of triangles. But basically, you're getting the point is you're getting positive contribution from the overestimates and the underestimates. Okay. What we show is that for For what we show is that there's a different notion of calibration, of weighted calibration, that we call proper calibration because it's derived from a certain class of proper loss functions. But the lemma that we show is that it's equivalent to some threshold weighted calibration. Okay, and I'm going to show you how this notion of weighted calibration behaves. Okay, whereas L1 calibration considers the the over and under estimates equally and both contributing positively, this notion of proper calibration treats them differently. Okay, it says the overestimates contribute positively and the underestimates contribute negatively. Okay, and so what do you look at? You have to find the worst threshold that you can find and look to the right of it or to the left. And now you add up your errors, not just not absolutely, but with signs. Okay, so again, being loose, maybe if we looked at this threshold, the only contribution that would remain if these things roughly cancel out is this small region here. Okay, so it's a new notion of calibration, and in fact, for the same set of predictions, the proper calibration error can be considerably smaller than the L1 calibration error. And what we show is that this notion of proper calibration is actually sufficient to achieve omniprediction. Okay, so whereas previous works achieved multi-accuracy plus calibration, plus L1 calibration implies omniprediction, we show that proper calibration suffices.
Was there a max over theta?
Yes, exactly.
So, but it's one-sided. You seem to indicate that
It-
go either way, probably.
It's one-sided, it could be two-sided, yeah.
Okay.
Yeah. The definition will be the same up to, a factor of 2.
Yeah.
And we're not worried about that here. Okay, so in the last few minutes, I want to tell you about how we turn this into a new algorithm for achieving omniprediction. Okay? So this proper calibration, it's a little bit of a mouthful, but basically you can write down this proper calibration as an online regret problem. Okay? Where for a sequence of y's and predictions, outcomes and predictions, the proper calibration regret is the worst case threshold choice times this y minus pt. Okay, so this is what we'll define as this regret. And you can view trying to achieve low regret on this notion of regret as a certain vector valued game. Okay, so vector payoffs, where the vectors, where the coordinates of the vector are indexed by a sign to handle this absolute value, as well as the choice of theta. Okay, choice of this threshold, and we'll discretize that threshold. Okay, but now I have a vector valued game, and I want to achieve sort of low regret with respect to this vector payoff. And it's a technique that I've learned recently, but it's a very classic technique. This is Blackwell approachability. Okay, so if you haven't heard of this, it's a kind of generalization of the minimax theorem. It's a generalization of playing zero-sum games with scalar valued payoffs. Here we can do it with this vector valued payoff and try to make this vector approach 0, so to speak. Okay, and so how is this going to go? It turns out that there's actually an algorithmic framework, connection between Blackwell and online learning discovered by Abernethy et al. Maybe about a decade and a half ago. That's very powerful. Okay, and what we can show is that there exists an online algorithm that achieves almost square root t regret for this proper calibration objective. Okay, how the online algorithm is going to go is that we define a coordinate for every one of our constraints. Every one of our proper calibration constraints, we have a coordinate. And we play multiplicative weights on those constraints, okay, to try to witness a violation of low proper calibration. Okay? Given the weights that we're playing, we can combine those weights and then choose an optimal play in order to hedge against different outcomes. Whether the next outcome is 1 or 0, we maintain the fact that our proper calibration error is not going to increase too much. Okay, it's a gross simplification, but really that's sort of what's going on under the algorithm. Okay, so this algorithm works for proper calibration. I told you we needed proper calibration plus multi-accuracy. It turns out that multi-accuracy can be viewed as also a set of linear constraints. And you can similarly play multiplicative weights on constraints defined by the hypotheses in your hypothesis class. Okay, so that's actually a pretty easy transition from achieving just proper calibration to proper calibration plus multi-accuracy. Of course, though, now I'm playing an online algorithm over every hypothesis in my class. It's rather inefficient. Okay, so what we show is that there's a way to sparsify this Blackwell algorithm, to sparsify and be able to get away with just using a learning oracle for this class H. Okay, so in the online algorithm, you need an online weak agnostic learner. We show how you can, and you can replace this in a conversion. So, but again, this is a pictorial representation of actually quite a subtle algorithm, but it boils down to playing multiplicative weights over the proper calibration constraints, some hypotheses that are returned to you from a learning oracle, and then combining them and playing a mixed strategy in a way to hedge against the different outcomes. Okay, so the very first theorem that I promised you, though, was an offline algorithm, was a distributional learning algorithm. And so naturally, we are going to use sort of an online to offline conversion. Okay, I gave you this near optimal algorithm for omniprediction in the online setting. Can we just take it offline? Okay, the problem with doing that is, at least in the way that we, in the most naive version of an online to offline conversion, what you end up with is inefficient omnipredictors at the end of the day. You can still learn them in a small number of samples, but your representation downstream is going to be inefficient. Okay, so actually a good amount of our forthcoming paper is actually figuring out how to run an online to offline conversion that maintains efficiency throughout the way. So that at the end of the day, the thing that we output is an omnipredictor from a small number of samples that is actually efficient to run. Okay, and efficient to learn along the way. Okay, so that's so sort of the report card, just to remind you, is that we show that this task of omniprediction, this task of simultaneously minimizing many, many different loss functions at the same time, can actually be achieved in very similar complexity to learning a single loss function, minimizing a single loss function. Okay, and we get this near optimal complexity on many different measures. Okay, I want to conclude with just sort of an open question or just open musing. Okay, there's we have our construction of omnipredictors in this work looks very different than prior constructions. Okay, prior constructions produced deterministic predictors that were based on a boosting kind of algorithm that used more samples and created circuits that look different than ours. I think as we understand this area better and better, we can start to ask really fine-grained and precise complexity questions about this problem. Are there trade-offs between sort of the complexity of representing omnipredictors and whether they're deterministic or randomized? And are there statistical trade-offs there? Is it possible to achieve near optimal sample complexity using it to learn a deterministic predictor? We don't know the answer to these questions, and I think there's a lot of interesting follow-up questions still. I think we're answering a lot of questions, but even in answering the questions that existed, I think we're opening even more questions. So yeah, hopefully some of you can figure out the answers to these questions. Yeah, thanks.
We're almost at time, so maybe we should end now. I think, because I think people are waiting for the next one. But thank you very much, Michael.
Yeah, thanks.
And you'll be here for the afternoon. So
Here for the afternoon.
If you want to meet with Michael, yeah.
Yeah, great talk.
Thanks. Yeah.